In this video we're going to look at identifying and understanding probability density functions. They often have the initials PDF in lowercase or uppercase. So when we've moved in our previous video from histograms to something that is hopefully a bit more substantial and something we can have more confidence in, we need to move from the left to the right of the screen, and you can see that we're going from a histogram with a polygon connecting the midpoints of all the columns to a smoother curve to a curve with some different units on it. And what we've done to do that, we need to increase the sample size, we need to increase the number of intervals quite a lot, which means we have a decreased interval width, and we need to basically arrive at a devised function that describes the probability distribution, and it can help us approximate or determine probabilities. Okay, and that's what we're talking about with probability density functions, because again we're talking about continuous variables, continuous random variables. So you can see on this diagram on the left is what we might have had in the previous video, and we got frequency versus what we were looking at in that one was mass. The polygon is a bit rough. If we increase the sample size and number of intervals, we get a smoother curve, and then we eventually replace the frequency with a function f of x. Okay, now a bit more on that. The absolute area, so we're not talking about signed area. You might refer to integration curves if you're a bit unsure about what they are, or if you've forgotten. The absolute area, so we're only looking at the size of the area, not whether it's above or below. Absolute area bounded by the curve, and the x-axis can have any value as long as it's greater than 0. Okay, and if the entire curve is scaled down so that it becomes one unit, it's called a probability density curve. So the standard probability density curve has an area of 1, regardless of what the area was prior to that. So this area here on this one is not 1, but it is by the time we get to our probability density curve, or our PDF. And this is again for a continuous random variable. Formalizing this, we have the probability of the random variable x being between limits a and b exclusive is given by the integral of the given function, okay, which is what we're moving towards, between terminals a and b. Okay, so we use integration, which having studied calculus, that should make sense. There's some conditions. One condition is that the curve itself is at least 0. Okay, so it's 0 or greater, so that line never drops below the x-axis. So the y value, or the f of x value, is always above 0, or at worst equal to 0, or at least equal to 0. Okay, and x has to be found in the interval between a and b. Alright, so the thing has to be at least as high as the x-axis or above. The next condition, for all possible values of x, it must be such that the sum of all the probabilities equals 1. So that means in a continuous curve from negative infinity to infinity, the area under the curve for the entire distribution equals 1, and that ties into that earlier point that the area under the curve for the entire curve has to equal 1. Two examples. Okay, consider the exponential probability density called f. It has this rule now. These rules are in a piecewise manner, and that's pretty normal. You'll get, generally with these questions, you'll get 2, sometimes 3 for the level we're looking at. So when x is greater than 0, it follows the function f of x equals 2e to the negative 2x. And otherwise, okay, you can see that these are complements, these domains. Otherwise, it equals 0. Okay, now we're going to sketch that. We're going to use technology to sketch this one. Okay, so I'm using a T1 Spire, so we get our templates for piecewise, which that one shall do. And I've double clicked that. I didn't mean to double click it. So for the first part, 2 times e to the, whoops, 2 times e to negative 2x when x is greater than 0. And then it's 0 otherwise. Oh. Like so. Okay. And I'm just going to zoom in on that a bit there. Okay, I'm making a lot of errors there, so I've just fixed that up. There we go. My apologies. So we can see the curve. See that 2 branches there? That one, if you were to draw that by hand, you'd have an open circle there. Okay, and the rest of it, 0 and below, sits on the x-axis. Okay, so that's our sketch for it. So for part B, showed that it is a probability density function. We said that, remember, f of x has to be at 0 or above, and we just showed that on the diagram. It always is. Okay, so remember the curve never goes below the y-axis being 0. Okay, in other words, f of x equals 0 is the lowest. Okay, it's always at least that. So that's the first condition. Second condition to be satisfied is that the area under the entire distribution equals 1. So that is basically, if you think about it, if you remember the graph from just a second ago, it's only that part from here. So if we go back, 2e to the negative 2x. So, whoops, I've got a 2 there. 2e to the negative 2x. The integral from 0 to infinity equals 1, because elsewhere, what's the value? Well, 0. Elsewhere it equals 0. So, because remember that curve hugged the x-axis, so the area elsewhere, see, is going to be 0. So that's basically irrelevant to our purposes here. So it's the limit as k approaches infinity for some value k. So as we get to that, we can't get to infinity, as you know, the nature of limits, but as we approach. So we have to use some of the work on our limits, which we might not have used for a little while. That's an important step. Now that equals the limit as k approaches infinity for that expression there, because we've taken the integral. So using our process of definite integrals, we have negative e to negative 2k minus negative e to the 0, and we've got to find the limit as k approaches infinity of that there. And let's have a look. Now that negative e to the negative 2k is negative e, whoops. Oh, I'm making a lot of mistakes in this video because I'm rushing. Now the infinity part, as k approaches infinity, only affects the first term, so I've just written it with a positive index. As k approaches infinity, that'll be e to the infinity, which is very, very big. So you'll have negative 1 over something really big, right? So that approaches 0, that whole term. So we have 0 plus e to the naught, and that equals 1. Okay, we're going to take a break there, and part 2 is coming right up, where we'll continue on.